So all of the continuity that we've done at this point in time have been open parentheses. And why has it been open parentheses? Well, let's think about that definition. You need to have the point exists, the limit exists, and those two things are the same thing. So let's look at the following graph at the square root of 3 minus x. I'm looking particularly when x equals 3. If you notice when x equals 3, certainly the point exists. If we come from the left of it, certainly the limit exists and it's the same thing as a point. But remember, for a limit to exist, you must have the limit from the left equals the limit from the right. Well, what's the problem? This function doesn't even exist to the right of x equals 3. So you can't say the limit as x approaches 3 of this function exists because there's no left and right to equal each other. There's only one side. Well, they make a special case for one-sided limits when it's not defined to the other side. So you would like to say it's continuous at x equals 3. We can draw it without lifting our pencil to x equals 3. But the question is, do you use a parenthesis around 3 or do you use the bracket around 3? And this thing right here, this definition of continuity on a closed interval, allows us to use a bracket in this unique case. So it says, let f be defined on a closed interval a to b. If f is continuous on the open interval ab, which we had no doubt about that, from negative infinity to 3 with parentheses, it was continuous. But the question is, can we use that bracket at 3? It says if the limit is x approaches a from the right-hand side of f of x equals f of a, and the limit is x approaches b from the left-hand side of f of x equals f of b, then f is continuous on the closed interval ab. Moreover, f is continuous from the right at a and continuous from the left at b. So what the heck did we just say? What we just said is we know this function is continuous on the interval, without a doubt, continuous on the interval negative infinity to 3 with parentheses, because we can draw it without lifting up our pencil, right? Okay. So the question is, what about at 3? What about at x equals 3? And so what this is saying we can do is we could look at the limit as x approaches 3 from the left of this function is equal to 0. And notice that f of 3 is equal to 0. So because we have those two things, we are able to include or able to imply that it's continuous from the left at x equals 3. So in other words, because the limit exists from the left is 0, the function exists at that point and it's 0, then we can say it's continuous from the left at x equals 3. In other words, what we can do is make our answer negative infinity to 3 with a bracket. So if the one-sided limit exists, the function exists, then we can put that point in a bracket. But that's a real deep dive using the actual thing. What should you guys do? Pretty much know that this happens when it comes down to radicals. Remember, whenever you're underneath a radical, whatever's underneath the radical has to be greater than or equal to 0. So if I look at 3 minus x is greater than or equal to 0, I'm going to subtract 3 from both sides. I'll have negative x is greater than or equal to negative 3. I'm going to divide both sides by negative 1. Remember, anytime you divide by a negative number, you need to swap your inequality. So this is going to be x is less than or equal to, well, negative 3 divided by negative 1 would be a positive 3. And so I'm thinking about my interval notation here. Here's the number 3. I'm shading to the left of it, and because it's less than or equal to, I can use the bracket. So that's how I got my answer, negative infinity to 3 with a bracket. So essentially this bracket, as far as we're concerned in this class, is only going to be used when we're dealing with radicals, when we have a one-sided limit and the function doesn't exist on the other side. So let's do that exact same strategy in example 4. It says determine the intervals of continuity of the function f of x equals the square root of x minus 2. So how do we handle radicals? Again, whatever's underneath the radical has to be greater than or equal to 0. So we have x minus 2 has to be greater than or equal to 0. Sorry, let me rewrite that. Greater than or equal to 0. So that means that add 2 to both sides. X has to be greater than or equal to 2. Think about your number line. Here's the number 2. We can include that number, and we shade it everywhere to the right. So our final answer is going to be bracket 2, comma. infinity. And if we looked at this graph, what this graph would look like would be something like this right here, where x equals 2, where it's not defined to the left of it, it's continuous to the right of it. We are able to include that point at x equals 2. We can use a bracket because the one-sided limit exists, the function exists, and they're the same at that point. Okay? We can also do this to determine intervals of continuity of piecewise defined functions here. Okay? Piecewise defined functions, again, we have some questions here. If I look at just the first function, x plus 2, that is a polynomial function. It's a linear function, which is a polynomial function. Polynomial functions are continuous everywhere, so that's certainly continuous from -1 to 3. And then 14 minus x squared, the other one, is also a polynomial function. It is continuous everywhere, so that's certainly continuous from 3 to 5. We can include the endpoints, -1 and 5 on this one, because we know it's continuous at those points. So the question then just becomes, is this piecewise function continuous when x equals 3? And as we talked about in the previous section, to find out if it's continuous, we need to know, does the function exist, does the limit exist, and are they the same thing? Well, the function certainly exists. The function is defined at x equals 3 right here when 3 is less than or equal to x is less than or equal to 5. So the function exists. Let's check to see if the limit exists. And if you remember, how do you find whether the limit exists on a polynomial function or not? Well, you plug that value in to both of the functions and you determine if those function values are the same. In other words, let's take at x equals 3, let's find f of 3. I really shouldn't even see f of 3. I'm going to take my first function, which is x plus 2, and I'm going to evaluate it at x equals 3. So that would be 3 plus 2, which is 5. So if I plug it into the blue function, the first function, I would get 5. Now let's look at 14 minus x squared at x equals 3. And of course I'm using x equals 3 because that's where I broke it up. That's where the piecewise function is broken up. So this would be 14 minus 3 squared. That's 14 minus 9, which is 5. Notice it's the same in the top function, the blue function, as it is in the bottom function, the red function. Since those are the same, that tells me the function exists, the limit exists, and they're the same. And if the function exists, the limit exists, and they're the same, I know it's continuous at that point. So it has to be continuous from -1 to 3 because x plus 2 is a polynomial. It has to be continuous from 3 to 5 because 14 minus x squared is a polynomial. And it is continuous at x equals 3 because those two values agree. Because of all of that, we can say it's continuous on the entire interval. We can't say -infinity to infinity because it's not defined on -infinity to infinity. It does start at the -1. We can use a bracket. And it goes all the way to the number positive 5, and we can use a bracket. Okay, if this were separate problems, we could say that this one was continuous on -1 to 3 with parentheses. And if this were continuous, we could say the second function was continuous from 3 to 5, both with brackets because they're both included. So the question is, what happens when we mash those two together? Can we include the number 3 or not? Again, we plugged 3 into both of them to figure it out. They did agree. Because they agree, we can just make it continuous directly from -1 to 5. Otherwise, we would have had to break it up into those two separate intervals.